Right, so we're going to look at the reactions of halogenoalkanes or haloalkanes. Now, I say reactions, but in fact, there is only one that you need to know about. And the reaction that you need to know for halogenoalkanes is that they can be reacted with hydroxide, in particular sodium hydroxide usually, although it could be potassium hydroxide, in aqueous solution to form alcohols. So simply, if we're just looking at reactants going to products there, you can see that we've got a halogenoalkane to bromopropane, reacting it with sodium hydroxide, and what's happened is the OH from the hydroxide has replaced the bromine, so it's in the same position as the bromine was. Bromine's gone, and so the other product would be sodium bromide. So that reaction would work with other halogenoalkanes. It doesn't matter whether it's bromine, chlorine, iodine, or the position on the carbon chain. The same type of reaction would happen. Now, the conditions, you usually do need to heat this, and we're going to look at the reaction in practice as best we can in this situation in a next lesson probably. So you'll see that actually sometimes it goes faster and sometimes it goes slower, so the heat sort of depends on that. But just as a general, what would you do? Heat is what you would quote for the conditions. And now you know about reflux, you can say heat under reflux, but not necessarily required to get a mark in an exam. Just heat would do. Now you do need to know the mechanism for this reaction. So if we look at how this is working, then if we've got our halogenoalkane, it's the hydroxide ion that's important here. And what happens is the hydroxide ion comes in to the carbon and forms a new bond. And the reason it does that is because of the nature of the carbon to halogen bond. So remember what we've said already is that because of the electronegativity of the halogen is always going to be delta minus. It pulls the electrons in the bond towards itself, leaving the carbon as a delta plus. So regardless of which halogenoalkane it is, that delta plus, delta minus is always present. The hydroxide ion has a lone pair of electrons available, and that lone pair of electrons is attracted to and forms a new bond to the delta plus carbon. So you may remember that a species which donates a pair of electrons is known as a nucleophile. So the hydroxide ion is behaving as a nucleophile here. Now obviously that carbon cannot then have 5 bonds, which it would have if we just left it like that. So a bond has to break, and it's the carbon to halogen bond that breaks. So starting at the bond, okay, not at one of the atoms, you're showing the movement of the pair of electrons that are in that bond to the bromine. So starting at the bond and going to the bromine is your second curly arrow there. Okay, and that's representing the fact that the carbon to bromine bond is breaking. The pair of electrons that are in that bond are both going to end up with the bromine, making it a bromide ion. Okay, it's gained 1 electron, hasn't it? Because it originally donated 1 electron to that bond, but it's now got the one that the carbon donated as well. So there's the new product, the alcohol, in this case propantuol, and a bromide ion. So just a couple of other points there at the bottom. As we've said already, the hydroxide ion is behaving as a nucleophile, so this is a nucleophilic reaction, and in particular it's a nucleophilic substitution. Okay, 2 reactants, 2 products, a group of atoms has replaced something else on our main organic molecule, so substitution, and it's nucleophilic because the hydroxide ion is acting as a nucleophile by donating a pair of electrons. And just another sort of point, just to sort of add in your technical language, just to explain what's going on in the mechanism. When that carbon to halogen bond breaks, the type of bond breaking is heterolytic fission, because remember, both electrons going to the one atom to produce an ion is what's called heterolytic fission rather than homolytic fission. So that is as I said, the only reaction that you need to know for the halogenoalkanes and the only mechanism, although we are going to look at a little bit more detail, as I said a moment ago, about the rate of this reaction. But we will do that next time.